Good afternoon, and thanks for everyone staying for this last session, which I'm sure is going to be well worth your time. Thanks for attending our conference this year. I hope that it's been a very productive time for everyone. My name's Cindy Duncan. I'm with AISC. This session is one of the top hits from Top Prof session P7, entitled Partially Restrained and Flexible Moment Connections. And our speaker will be Dr. Louis F. Geschwinder. Louis Geschwinder is the Vice President of Engineering and Research of AISC. He's also Professor Emeritus of Architectural Engineering at the Pennsylvania State University, otherwise known as Penn State. He received his bachelor's degree in Building Science from Rensselaer Polytechnic Institute and both his Master of Science in Architectural Engineering and his PhD in Civil Engineering from Penn State. He is a registered professional engineer and was a faculty member at Penn State for more than 35 years, teaching and conducting research in building structures. Professor Geschwinder is the past chairman of the Metals Technical Activities Committee and also the Committee on Design of Steel Building Structures of the Structural Engineering Institute of ASCE. And he is currently a member of the AISC Committee on Specifications, which approves our main specification as well as our seismic provisions. He also chairs our Member Design Technical Committee. Dr. Geschwinder has been the author and presenter of many AISC lecture series. You may have seen him present before, and he was the winner of the T.R. Higgins Award in 2000. It is my pleasure to welcome Dr. Louis Geschwinder to the stage. Please join me.
Thank you, Cindy, and thank you all for coming. As you can see, being vice president doesn't get me a particularly high standing on assigned sessions. Very end and very tired. So as I usually say after lunch when I'm doing the new specs seminar, I'm going to rely on the guys in the front row to wake me up if I fall asleep when I'm up here. I hope you've found this to be a good conference. Everything that we've heard, it's been a good conference, and we're very pleased with that. And I hope you will find what I have to present this afternoon to be of interest. I looked at this opportunity when I was asked if I would do this to try and figure out, what kinds of things could I talk about. And I thought it would be a good idea to talk about partially restrained connections or semi-rigid connections or flexible moment connections, whatever terms you're used to using, and go back to the beginning and talk about a little bit of the behavioral aspects of it, and then bring it up to date and talk about a method that you might use to get a start on using these kinds of connections. In terms of background, the AISC specification first recognized in any kind of a definitive way the various ways of a connection to behave in 1946, and that's when the types of construction were first defined in our specification. And those types of construction, type 1, type 2, and type 3, remained the designations right up through the 1989 ASD specification. So a type 1 construction was a construction with rigid connections, moment frames, rigid frames, again, a whole series of terms that you can use to identify them, but type 1, rigid. Type 2, defined as simple connections, or frames with simple connections. And type 3, semi-rigid. Now type 3, semi-rigid, required, all the way along throughout its use, required that you understand and that you know the actual connection moment rotation characteristics. Type 1 was an assumption, a simplifying assumption, that the connection was perfectly rigid, no moment, full moment, no rotation. And type 2, most of the time, a perfectly simple beam rotation and no moment. Unless, of course, you used that wonderful system called Type 2 with wind. And as Bob Disquay, Mr. Steele, Mr. AISC, was fond of saying, that was certainly valid west of the Hudson River. Excuse me, east of the Hudson River. We weren't quite sure about whether it jumped over the river or not. But it was a method that was used and has been used. So we'll talk a little bit about Type 2 with wind down the road. Now, when we got to the 1986 LRFD specification, and then right up through the 1999 LRFD specification, Specification Committee chose to redefine the types of construction. And so they defined Type FR, which was fully restrained, right, rigid connections, and Type PR, which was everything else. PR representing partially restrained. And they said that the simple beam, the simple pin connection, was a special case of the PR connection. Okay? Now, as we talk more about this, it'll be pretty clear that if a simple connection is a special case of PR, so is a rigid connection, just at the other end. But that's what the LRFD spec had. In 2005, of course, we've combined provisions so that we now have one standard, and I expect you're all fully familiar with the 2005 spec and are designing with it every day now, right? And if you haven't purchased the 13th edition manual, just get online and order it. You know, I can't believe that you can still sell a 9th edition manual on eBay for over $150. But you really don't want to go buy that. Get yourself a 13th edition. With this specification now, the committee realized that it was kind of a stretch to only consider simple connections as a special case of partially restrained. And so in section B3.6a, the specification now defines simple connections. And in B3.6b, it defines moment connections, and under moment connections, fully restrained and partially restrained. Now, if we look back to get a feel for how were connections used in the analysis, and then after subsequently in the design, how did we actually do it? One of the early references that we find was published in 1915, and it's 6 monographs on wind stresses. Back then, of course, we didn't have our computers. We didn't even have moment distribution. And so indeterminate analysis, what you were going to do if you had a moment frame, for instance, relied on the portal method or the cantilever method. And it relied on just simple beam design for gravity loads. And that's the start of an approach that became known as Type 2 with wind. In 1949, we had a paper that actually talked about how frames responded if they had semi-rigid connections, or partially restrained, although that wasn't the terminology at the time. And then in 64, Disquay presented an article in the AISC Engineering Journal where he talked about smart connections. Now, these were the connections designed under the system called Type 2 with wind. They were connections that knew when they were carrying gravity load, they were not to carry any moment, but when the wind blew, they were to carry moment. Okay? And if you talk to Bob, he will continually tell you that there are many well-performing buildings out there that were designed by that approach. And I'm not going to talk about any of those buildings or try to justify the use of anything because it has worked in the past. But I want to talk about how these things are going to behave and how we can view the analysis. When we look at PR connections or Type 3 connections, we're talking about typical connections that you use. They might be flush end plates or just flange angles or double web angles or flange plates or any connection that you can think of that might not be perfectly rigid, but would resist some moment even though they allow some relative rotation. If we look at, are there any advantages to using these kinds of connections? These are potentially advantages. They may be overall more economical. They may reduce the total weight of steel in your structure. They may be simpler to fabricate and to erect when compared to fully restrained. And you might even be able to get moment capacity without having any kind of a welding component to that connection. So those might be some advantages. The disadvantages to these kinds of connections, however, is that the analysis can be rather complex, because these connections, as we'll see in a little bit, are not going to behave linearly. The loading sequence can be important. And so you'd have to start thinking about, all right, how do I put the loads on this building, and how much dead load and how much live load, and in what sequences and all. If these connections permit rotation, then as part of a lateral load resisting system, they're going to permit more drift than if they had been fully restrained connections, because the drift is going to be a result of the angle now that in the past would have been 90 degrees, or as an FR connection, 90 degrees. And perhaps the bottom line in terms of considering the disadvantages is that you really do need to know the true connection behavior. You need a moment rotation curve that predicts exactly what's going on. We can't just assume simple or fixed. Now, why haven't more people used these? One of the first AISC conferences that I went to was here in Nashville, out at Opryland. I don't remember how long ago it was, but I do remember that at that conference, Stan Lindsay presented the use of partially restrained connections in the design of steel structures. And he was perhaps the only one, the only firm that was consistently using PR connections, and he felt that they, in fact, were an economical way to go. But over that entire period of time, there has not been a whole lot of increase in the use of these kinds of connections. And I've identified three things here that I think perhaps could be considered the deterrents to any expanded use. And the first is the lack of authoritative literature on the approach, which means, of course, no clear guidance. No idea if they really are practical or more economical. And there really is no commercially available software. You can't just pick up that software you're using for everything else and real easy put in these connections. Well, AISC could probably be to blame for not providing any of those things. But if you look back at what we have done, we have had quite a few studies looking at connection design, looking at fabricators estimating the cost of the PR versus the FR frames, and we could not come to any firm conclusion that, yes, these are better, yes, these are more economical. We didn't come to the conclusion that, no, they're not better, and no, they're not more economical either. So there just isn't a good set of conclusions. And so that means if you're going to consider using these kinds of connections, you have to determine for yourself if there is any advantage to it. Now, the presentation basically is founded on two papers. The first one, a simplified look at partially restrained beams, that was published in the 1991 Engineering Journal, second quarter. And of course, you all know, if you're a member of AISC, you can download all of the EJ papers for free. All right? So I encourage you, if you have any interest in this, go back and download the paper and take a look at it. So we're going to look at the basic theory, and we're going to consider first, how does a beam behave if it has a flexible connection on the end, a partially restrained or semi-rigid connection. Then we're going to look a little bit at how the connection behaves, and then we're going to put the two of them together. So the first thing we're going to determine is there any way to get an advantage in the design of the beam? Okay? And that's what that first paper addresses. So if you just take a beam, and if you think back to your classical methods of indeterminate analysis, and if you're old enough, you can take all the classical methods because that's what they taught you, right? Classical methods like slope deflection, you remember that? And you can write these equations. If you take a segment and you put a moment on each end, and each end rotates, the moment on the end, MA, is equal to 4EI over L times theta A plus 2EI over L times theta B. And that's just the slope deflection equation. And of course, if we take a fixed-ended beam with a uniform load, we know that the fixed-end moments are WL squared over 12. And if we combine them, and we recognize that the rotation at B is equal and opposite to the rotation at A, superimposing these, we find that the moment at A is 2EI over L times theta minus WL squared over 12. Okay, so there's a very simple equation to represent how that beam would behave. Now let's look at the special cases. If it's a simple beam, the moment at A is 0, right? And so you can solve the equation, and you get theta is equal to WL cubed over 24EI. And this is the simple beam rotation. And if you look at the fixed-ended beam, which we, of course, started with and know this answer already, if you put theta equals 0, the moment at A is minus WL squared over 12. So we can plot that. All right? So we have the rotation down here and the moment here. We plot the fixed-end moment, WL squared over 12, the simple beam rotation, WL cubed over 24EI, and the slope deflection equation is that straight line. So we immediately see that as the rotation on the end of the beam changes, the moment on the end of the beam changes. Okay? Now, let's look at the connection. Okay? So we've got a beam and it's framing into a little spiral here, which is the connection. And the moment in the connection is the stiffness times the rotation of the connection. All right, so that's the connection. And if we plot that on that same moment rotation diagram, it's simply that straight line. Now, saying it's a straight line is a critical thing because we're making the assumption that the connection behaves linearly. Okay? And that is not going to be the case. But for now, we'll look at that as a linear connection. This is a real connection. Okay? This is a double angle web connection with a top angle and a bottom angle. And it's just one that I pulled out of the proceedings of a connections conference a few years ago. And I have it to show that the connection behavior, right, moment, rotation, doesn't look anything like that straight line that I gave you. Okay? Maybe if we're down here, you could say, well, that's approximately a straight line. And of course, if we expanded the horizontal scale, maybe we could see that. The other thing to show with this connection is that it gets up to some point, and in this case, we had bolt failure. All right? So this connection does not just go on forever. So we have to look at our connections, recognize that the real ones are not linear behaving, and potentially they could have a failure, something that would give you an abrupt failure. So keep that in mind as we go through this. This represents perhaps a better picture of the connection. Okay? Not a straight line, but some kind of a curve. And if we superimpose then the beam line and the straight line connection, we find equilibrium right there. Okay? So if we set these two equal, we can determine first what's the rotation at that point of equilibrium. So this is simple beam rotation. This ratio simply represents a multiplier to give you what reduced amount of rotation, or reduced amount of rotation am I going to get. And if the spring stiffness approaches infinity, in other words, a vertical line, then of course the rotation goes to 0. If we do it the other way and determine the moment, we can solve the beam equation for the rotation and the connection equation for the rotation and set them equal, and we get the moment on the connection is the moment on the beam is just the moment m, is equal to, again, the fixed end moment times 1 over 1 plus 2EI over NL. That EI over L divided by N is a ratio of the beam stiffness to the connection stiffness. And so in the paper and here in the slides, I've called that U. Anyone could have come up with any letter, so if you read other papers on similar topics, you might find that referred to as alpha or whatever someone wanted to use. But keep in mind that all we're looking at is the ratio of the beam stiffness to the connection stiffness. And so if we substitute that into our equation for the connection moment, or the moment on the end of the beam, you see we have the fixed end moment divided by 2u plus 1. So now we have a very simple little connection moment equation. If we keep with our uniform loaded beam, so that the WL squared over 12 fixed end moment, and we solve for the moment at the center line, we end up with this equation. All right, so again, it's a function of the beam to connection stiffness. And if we plot that, looking at a linear connection and gravity loads, in this case, the uniform load on the beam, you see that the connection moment, or the negative moment, starts out when the stiffness ratio U is 0. We start out with 1, which is the moment over the fixed end moment. In other words, here we're talking about the fixed end moment. And as that stiffness ratio increases, the moment on the end of the beam decreases. At the same time the moment on the end of the beam is decreasing, the moment at the center line is increasing. And so we have WL squared over 12 at the end, we have WL squared over 24 at the center line. And as U increases, the center line moment goes up. Now, at a U of infinity, the end moment is going to be 0, and the center line moment is going to be WL squared over 8, right? And that's simply 1.5 times the fixed end moment. Now, the important thing about this diagram is that it shows what is happening to the beam. And it shows that no matter what you do, no matter what kind of linear connection you have on the end of this beam, you're never going to be able to design the beam for a moment less than that value right there. Right? Because if you're down here, the end moment is higher. And if you're from here out, in terms of the stiffness ratio, the center line moment is higher. All right? So that beam for gravity load, uniform gravity load, is going to be designed for WL squared over 16, the absolute best case scenario. And if you think about plastic analysis, and you do remember that although we always talk about the ASD specification, it really wasn't the ASD specification, it was the ASD and plastic specification, right? And if you look at that, the plastic mechanism for the beam, which again gives you the best possibility for the beam, puts WL squared over 16 at each end, and WL squared over 16 at the center line, and you end up with a collapse mechanism. Okay, so you could get at that same conclusion a number of different ways. So no matter what we do with a connection, if it's a linear connection, that's what we're going to work with. Now let's say we take that connection and we put it between our uniformly loaded beam and another beam at each end. And it could be a beam, it could be a column, it could be any kind of a structure that we connect it to. But if we connect to another structure, the effective spring stiffness can be determined. And the effective 1 over the effective spring stiffness is simply 1 over the actual spring stiffness plus the stiffness of this backspan, which if the back end is fixed, like here and over there, then it's the length of the beam, the length of that backspan beam, over 4EI of that backspan beam. Okay? So we can come up with an effective spring stiffness and then go right back to the same model that we had before and simply say that is our effective linear spring. Now what I've done here, however, is overlay a closer PR connection curve, one that isn't linear. So maybe it really does that. It could do anything it wants. It could come up here and go down there and then go up there. It doesn't matter where equilibrium is, because equilibrium is right there. If the curve goes through there or the straight line goes through there. So again, we come back to the same behavior for the beam. All right? So whether that central section, which was the uniformly loaded beam, is just attached to 2 linear springs, or it's attached to 2 linear springs which are then attached to 2 beams or to 2 columns or to a whole structure. And even if the connection is not linear, but we know the secant stiffness, right, the straight line that connects 0 to the point of equilibrium, we're back to knowing the exact behavior of that beam. I hope they don't have any flexible connections over there. Okay, so let's look at connection curves. This is the one that I showed you just a minute ago, just some arbitrary curve. We called it a PR curve. A fixed connection, or an FR, or a type 1, would probably look something like this one. All right? Probably there will be some rotation. But the model that we use is this straight line, right? We're assuming that there is 0 rotation no matter what the moment is. At the other end, we've got a curve that looks something like this. And we might call that a simple connection. The model, we're down here assuming no matter how much rotation I have, there's no moment. So how do we know whether that's really an FR connection and that's really a simple connection? If we superimpose the beam line, we have a way of measuring whether these things are behaving sufficiently close to rigid or sufficiently close to pinned. And Omar Bludgett, in Design of Welded Structures, indicates that as long as the connection can resist at least 90% of the fixed end moment, it's okay to call it a fixed connection or a rigid connection. And so that's what I've shown here. That connection, no matter how we get there, excuse me, under the service loads, or the loads that it's actually feeling, as long as it takes 90% of the fixed end moment, it's going to be a fixed connection. At the other end, he indicates that as long as the connection doesn't take more than 20% of the fixed end moment, we can consider that a simple connection. Excuse me. So that's what I've shown down here. This is 20% of the fixed end moment. This is 90% of the fixed end moment. Of course, there are corresponding rotations to that. And in this case, the graphic that I've used simply shows a moment rotation curve that comes in at 50% of the fixed end moment. And that one we would say, well, that is such that we have to know its actual behavior in order to do anything with it. Down here, though, anything down here, we'd be okay. We call it simple. And anything up here, we'd be okay if we called it rigid. So let's draw those straight lines and see what that means. If you take that straight line up to 90% of the fixed end moment, what you find is that if Ks is the secant stiffness of the connection, right? In other words, no matter how the curve goes, that's the point we're at for equilibrium, then the relationship Ks times L over EI equals 18. And that would be considered a fixed connection. Now that's the inverse of what I was looking at before with U, okay? And there's a reason for doing this, and I'll tell you in a minute. If we go down to the other end, at the simple connection, that ratio is 0.5. And then the one I had in the middle at 50%, that ratio is 2. All right, now, I don't know whether Omer Bludgett's the first one to say that 90% and the 20%, but I do know in his 1966, that's what he said. But what I found was that the commentary to the 2005 specification gives 20 for that number, and it gives 2 for that number, which bumps it up to here. And so as a result, and the whole reason for pointing that out is I do believe there's a typographical error in the commentary, okay? Because I went back to the paper that the commentary references, and the paper is looking at 0.5, okay? So if you're reading through the commentary on connection behavior, it says look at your connection stiffness, look at your beam stiffness, and if your ratio is between, now we know, 0.5 and 18 or 20, you would want to consider that to be a semi-rigid connection. All right, that was a beam. All right, and we did it for a uniform load, but you could just as easily do it for a concentrated load or any other kind of loading as long as it was symmetric. And as soon as you move away from symmetric, then you have to solve both ends of the beam, and it's just more complicated than we need to talk about today. But now let's put those connections in a little lateral load resisting system. All right, so we've got this one-story, one-bay frame, and it's got connections at B and B prime, and those could either be PR connections or FR connections. They aren't going to be simple, because if they're simple connections, it's laying on the ground, right? So they have to have some moment capacity. We don't even need to know what those connections are capable of doing, as long as it's symmetric, to know that that horizontal force H is distributed H over 2 and H over 2. So this is a fairly simple thing to analyze. If we combine that now with a beam that has a uniform load, okay, put a uniform load on that beam, and you know that the ends are going to rotate, just like we've discussed, and you're going to get equilibrium right here. There's your beam line, there's your connection line, there's equilibrium. And then put on a little bit of lateral load. And what happens? Well, one of the connections is going to have the moment increased, and the other connection is going to have the moment decreased, right? And so you start out with two parallel columns and it moves sideways, all right? And this connection on that side opens up. The gravity load made it close up. The lateral load made it open up, so that one the moment in the connection is reduced. That's point B. And on the other end, the moment or the displacement due to the lateral load and due to the gravity load are going in the same direction, and so that moves us out here to point B. Now, what happens if I take the lateral load off? Well, it just goes back to A and A prime, right? Now, what happens if I decide to put 1.5 times H on there? Well, we just simply move out a little bit further. And if I take that load off, I'm back to A and A prime. So I can combine the gravity load and the lateral load with the flexible, semi-rigid connections, and as long as the connection is behaving elastically or linearly, I just move out and back and out and back, and I just keep going along like that, right? And that would make life pretty simple. But of course, we've already talked about the fact that the connections don't do that. So we need some kind of a model for the connection. I mean, we could build it and test it and plot it, but we'd have to do that for every single connection. And so when we start talking about, do we understand how the connections actually behave, we can go to equations like this, and this is called the three-parameter power model. There are any number of different equations for different kinds of connections. And there are two major sources for databases on connection behavior, both of them published in the 1980s. One of them published by Arvind Govardhan, who worked for Stan Lindsay and Associates. One of them published by Kishi and Chen, faculty and a graduate student, I believe, at the time. So we could look at this data, develop equations or use other people's equations. In that particular equation, we start out with the initial stiffness and then an exponent. Now this n is different than the n that I was using for the connection stiffness. Okay? It's the exponent here in this equation. We have some kind of a reference rotation which relates the ultimate connection capacity to the initial stiffness. So that's one way to describe a connection. And now let's look at how that connection behaves. Okay, if we put that connection on the end of both ends of the beam with the gravity load and the lateral load, we start out at point A, A prime. And we put on some lateral load, and one of the connections decreases the moment and the other increases the moment. Well, the one that the moment increases has to follow the connection curve, and so we go all the way up there to B prime. But the normal behavior of these connections upon unloading is to follow the initial stiffness. And so the unloading comes down this straight line. So where in the linear equation or linear connection we simply moved out and in all along that straight line, in the truer representation of the connection, the one side moves out along the curve, the other side unloads down the straight line. All right, now take off half of the lateral load. Well, if I take off half of the lateral load, the connection on the prime side, which is the one that was increasing due to the lateral load, now decreases along the straight line, the unloading initial stiffness. The one that had unloaded down to here now loads back up to C. But notice that now that is a linear behavior. So now we're at C and C prime. Okay? Take the rest of the lateral load off. So now all we have is gravity load. And look at what happens. We go from C back to D, which is where we had originally started on the windward side. and we go from C prime down to D prime because it unloads. Now put the lateral load on in the other direction. And the ABCD side now loads, so it moves up to here. And the prime side unloads, so it moves from D down to E, D prime down to E prime. Well, then you take some of that off, and we're back on this straight line part. Taking it off moves us up there. And if we keep going, and if we get beyond the point where the maximum lateral load that this system is ever going to feel, the system has gone through what is called shakedown. And in that situation, the connection is behaving linearly. Once it's gone through all of that permanent deformation, the connection behaves linearly. Now there's a major concern when you get to this point. And that is, remember that connection that I showed you that went way up that curve, looked just like this curve, and then there was a bolt failure? Most of the model equations make it appear that the connection just goes on forever. They're just equations. They don't say, okay, it ends here. And we have to be careful when we design any of these connections to make sure they behave the way we're expecting them to behave. Okay? But the whole idea of shakedown is that that connection, after it goes through this inelastic behavior, gets to a point where the loading and the unloading never exceeds the maximum that we already had on it, and therefore can behave elastically. The problem with trying to use that behavior in a real design, because it's not a linear behavior, we have to look at all these different load cases and try to figure out, what is the practical approach. And the same thing goes in any kind of nonlinear behavior. So it seemed that some kind of a simplified approach might help us to gain some appreciation for how these connections behave, and perhaps give us some opportunity to use partially restrained connections. And the approach then that we're going to talk about is generally referred to as the flexible moment connections. And this was now going to take these partially restrained connections, same kinds of connections we had before, and see if we can use them. And it is the next generation, if you will, of the old type 2 with wind. And in that old type 2 with wind, there were really only two things that you did. You designed the beams as simple beams, and you designed the connections for the moment due to the lateral load. And that was it. Now we know a lot more about how structures behave now than we did when this type of an approach first came about. And so what we're going to look at is, can we bring more of these things to bear on this problem? So this portion is based on a paper that I wrote with Bob Disquay called Flexible Moment Connections for Unbraced Frames Subject to Lateral Forces, a Return to Simplicity. This was published in 2005 in the Engineering Journal. And as we look at the design issues, we have to make sure we end up with a structure that has sufficient strength. And we have to make sure that we end up with a structure that has sufficient stiffness. And we have to have a structure that provides for stability. Okay? And so that's what we're trying to do here with this flexible moment connection approach. So we're looking at strength, we've got lateral load and gravity load. When we look at stiffness, we've got drift. When we look at stability, we've got the columns and the whole system. And so we've got this little 4-bay, 2-story structure. It's been covered in the literature several times, and so we're just going to use that as an example. And we're going to assume a certain kind of connection behavior. Okay? And this connection is going to be designed just for the lateral load moment. But no matter what you do, you have to make sure that no matter what load is on it, lateral and gravity combined, it's got to behave in the way you're modeling it. And we run into trouble when we use some of the model equations because, as I said before, and like on that picture, if you don't pick up the fact that you get to a point and one of the bolts fail or some other limit state occurs, if you get too far out there, you're not going to have the behavior that you expect. So we're looking at a connection here that's going to have a plastic moment capacity as its ultimate strength. Now we're still going to design the beams as simple beams. And if you go back to the earlier discussion, you realize that no matter what happens on the end of that beam, it's never going to be worse than the simple beam moment. In fact, that is the worst situation for the beam, right? So no matter what happens with the gravity load, the simple beam moment is going to be the largest. And then we look at the lateral load and say, okay, how are we going to distribute the lateral load? And so we're going to take a portal method type approach, and we're going to distribute that lateral load to the columns. But we're going to distribute it in a little bit different way. We're going to assume that the lateral load is going to add moment to the connection on the leeward side, and therefore the connection is going to behave plastically. And so we're going to put a hinge on the end of the beam. So we end up with a column here and a beam connected here through a flexible connection, a semi-rigid connection, but because of the way the loading is on it, this one is not going to be up there at the plastic hinge. It's going to be down in the elastic region because the lateral load is unloading. So I've got a rigid connection here and a plastic hinge over there. And each panel is the same thing, column and one beam, column and one beam. And so what we end up with over here is that's a pin-ended column with a beam pin connected to it, so it's not going to help in resisting the lateral load. So instead of taking the typical portal method, which would divide the lateral load into one part, two parts, and one part, we simply divide the lateral load into equal parts, ignoring the leeward column. Now, how do we design the columns? Well, we can design the columns for tributary area for the gravity load and the lateral load moment that we just calculated based on that distribution. We design the connections for the lateral load moment. And as we've already said, the beams are designed for the gravity load moment. Now let's look at the strength of the resulting system. What might we expect to see? If you look at the plastic mechanism that might occur for the gravity load system, okay, the beam mechanism is going to occur when you get WL squared over 16 at the ends and in the middle, right? We saw that already. And that is certainly going to have more strength than what we designed the beam for. We designed the beam for WL squared over 8. The beam is only going to feel with a plastic mechanism WL squared over 16. So the beam is going to be strong enough. If we look at the lateral load mechanism, we designed it for one less column, one less connection, if you will, than we actually have. And so, again, the lateral load mechanism should be good. And if we put the two of them together, the lateral load and the gravity load, if we remember that we have reduced factors on our loads, then you can show that the combined mechanism should be sufficient. Now let's look at the stiffness part of it. That was a look at a simplified approach to the strength. Now let's look at the stiffness. The 1989 ASD specification said that the connection and the connected members have adequate capacity to resist the wind moments. Now some people took that to mean that it didn't have to have any capacity to resist the gravity moments. Okay, there's been a lot of misinterpretation of that statement. If you look at what it said in the 1999 LRFD specification, it said the connections and the connected members must be adequate to resist the factored lateral loads. And some people interpreted that to be something different than what we had in 1989. I'm not sure that either one of them meant we could ignore anything. I think they were both trying to tell us you have to resist all of the loads that are going to be on your structure. So if we look at the 2005 specification, it says the forces and deformation used in design shall be consistent with the intended performance of the connection and the assumptions used in the structural analysis. That's pretty clear, right? No matter what, it has to behave the way you assumed it was going to behave in your analysis. So assume how it's going to behave, analyze it, design it, and make sure it behaves the way you assumed. That's basically what we're working under with the 2005 specification. So as we look back to what other people were doing, we found that the British had an approach similar to this, where they would design the beam for the gravity load and then have a simplified approach to the connections. And when they looked at the stiffness issues, they simply took a multiplier of 1.5. They said, just analyze the structure as a rigid frame and then multiply the deflection by 1.5. Now that works, but you have to recognize that they have a specific set of connections for which this system could be used. So as long as you're going to use their connections, their studies have said this will work. Another approach would be to put a linear flexible connection in there and do some kind of a computer analysis or do a real work study. But that requires, of course, either the linear connection or, if you wanted to go even further, the true connection curve. But there are certainly techniques that would allow you to get a more accurate answer. But what I was looking for here is, again, a simplified approach to it can get us close to where we might want to be in the end. Another reference on connection stiffness is this paper by Kim and Chen, again in the AISC Engineering Journal, and they gave some measures of connection stiffness. So we're going to use an approach there to see if we can figure out how our building drifts. And then we look at stability. Now, of course, how you approach stability is a function of the specification that you're using. The 2005 specification has some new approaches. The direct analysis method, the 99 LRFD or the 89 ASD use the effective length method and some kind of a second order multiplier if you didn't do a complete second order analysis. So what we're going to do here is use the effective length, look at the end restraints, look at things like leaning columns, which are gravity-only columns that are not participating in the lateral load resisting system, and then look at the overall stability of the system. If we assume that the loading end of the beam has the plastic hinge and the unloading end of the beam is rigid, this is the model that we have. So these are the same pins that we had before in that simple system. If we use the alignment chart, we can get an effective length factor. And when you have a beam where the far end is pinned, in the stiffness ratio, you use twice the length of the beam. Okay, now on every one of these columns, we've only got one beam coming in that's rigidly connected. All right, the beam on the, in this case, the left side was pinned. The beam on the right side is fixed to the column, pinned at the far end. Now, this is effectively using 1/2 of the EI over L of the girder. Okay, and that's a number that you want to keep in mind because we're going to compare that in a little bit. Driscoll presented a paper in 1976 where he looked at determining that stiffness ratio when you have beams connected with semi-rigid connections. And he calculated this term sigma C star, and that is the same as sigma I over L, sigma EI over L of the girders, okay? And he looked at 3 types of connections: type A, which is just a double angle connection; type B, which is a top and seat angle connection; and type C, which is the top and seat angle connection with the web connection. And he found that for a beam with those connections on each end, the type A connection, right, that's just the double angle web connection, worked as if it was anywhere from 0.2 to 0.76 of a rigidly connected beam. The type B connections, 0.96 to 1.72, and the type C connection, 1.5 to 1.7. Now, if they were fully restrained connections, what would we expect that number to be? 2, right? One beam from each side, fully restrained at both ends, we'd have 2 beams. So clearly, a type A connection, a double web angle connection, doesn't provide a whole lot of restraint to the column. And a type C connection may be very close to a rigid connection. The flexible moment connection approach, where we use one beam on one side at a length twice what it really is essentially 0.5. So if we plot this and look at how the equivalent number of girders relates to the stiffness ratio that we talked about before, you see for the double angle web connection you have a range here. For the type B, right, top and bottom, the range is from here up to here. And for the type C, the range is that little piece right there. So if we're down here, U is very small. That's pretty close to being a fixed connection. If we're in that range, certainly semi-rigid. And the type A approach, which assumed simply that the far end was pinned and the near end was fixed on one girder framing into the column, is right here. So what that means is that the approach that we're looking at is conservative for all but the most flexible connections. All right, in the range of the double angle web connection, this is basically right in the middle. So it's probably not too bad an approach in terms of reflecting how these kinds of connections would behave. So it's conservative for all but the most flexible connections. Now, when we talk about leaning columns or any other factors that have to be included, we would include them the same way we would in any other kind of a system. There have been a number of studies that looked at the type 2 with wind approach without the stiffness and the stability checks, simply the beam design and the connection design approach. Study done by Mike Ackroyd indicated that these structures should be limited to 10 stories. If you take the studies for the British system, they simply said from 2 stories to 4 stories and from 2 bays to 4 bays. And so they had a very narrowly defined system. With this approach, we're checking drift and we're checking stability. And so we're trying to look at these limitations. Look at the factors that led to these limitations. So let's look at this particular structure. And this is the same structure that's in the paper if you want to go take a look at what the numbers all actually mean. We took the roof girders and used the LRFD load combinations, got our shear, got our moment, and simply selected a W16 by 31 simple beam design. Same thing with the floor girders, and selected a W18 by 46. Again, just a simple beam design. Then we looked at the lateral force analysis. Remember, this example, as I mentioned earlier, comes from other papers in the literature, so we took the lateral load and we amplified it by 1.6, so these are the amplified loads for that load combination. We got the lateral load at the roof and at the floor, determined the shear in the beam, that's the 1.92 kips. Remember, we know how we're distributing it because we're distributing it equally to each column except the last column. And so the moment in the connection then is that 1.92 kip force times the length of the beam. So we have a moment in the connection of 48 foot kips. Then we looked at the column design for strength under gravity load and the moment that came from the lateral load, because whether the moment is coming from a lateral load or coming from the gravity load, the connection really isn't that smart connection that Bob Disquay had talked about. It doesn't really know, it doesn't take moment. So it's going to have that amount of moment in it. So we took that 48 foot kip moment and we tried a W10 by 39. And if you look at the in-plane sway and the alignment chart, with the beam twice as long as it really is, we determined the K factor in the plane of the frame is 2.12, and we compared that KL for the x-axis versus KL for the y-axis, and the y-axis controlled at 15 feet. And so we determined the axial strength based on 15 feet, the bending strength based on an unbraced length of 15 feet. Considered the second order effects, and the paper will show how the calculation of the B1 worked, but there was no amplification for the second order effects. And when we use the interaction equation, there's the applied load, the applied moment, and the strengths, we found that the ratio was 0.9, was less than 1. So for that load case, it looks like this system would be adequate in this simplified approach. Look at column design for strength under the lateral load. Now we have a different load combination, and our axial force in the column is 105 kips. And now I took that moment, it's the same moment, but now I said it's a lateral load moment instead of a no translation moment, so we're going to amplify it with the B2. And the other part of this is we have to figure out how to deal with that leaning column. And the approach recommended by Joe Ura as one possibility is to make sure that all the columns in the lateral load resisting system can carry all the load, which means we just don't worry about that last column. We'll put all the load on our 4 columns. And so if we do that, we can calculate the amplification factor, and you see we get a 33% amplification. We apply that to the moment, go to the interaction equation, and in this case, it's a lower value than we had for the gravity-only combination. So it appears that the W10 by 39 is adequate for this loading case. Then we get to the connections, and this is a critical part. And I'm not sure, frankly, that these connections actually work, because we did not go in and check to see whether any other limit state might end them. We were using the equation that I showed earlier, the three-parameter power model. But if you design for the moments that we had, this is the connection you get at the roof level, and that's the connection that you get at the floor level. Then we look at drift. And I did a rigid frame analysis. Now the beams, remember, were designed for simple beam moments. The columns were designed for this distribution of lateral load that we showed. Now I've gone back and said, okay, let's assume that we have rigid connections. Let's figure out the drift of this under 1.0 times the lateral load, and I get 0.63 inches. We have to figure out what can we do about that. Well, if we were considering that the British approach might apply, we'd multiply by 1.5. And that would give us a deflection of 0.95 inches. And that's less than an arbitrary limit of h over 300. So you might determine that that looks pretty good. You might say it isn't. You might decide that h over 400 is a better number. Whatever number, you get some idea as to what that connection would do. Another approach would be to use a linear connection stiffness. And if you take the ones from Kim and Chen and you get these two connection stiffnesses and get a calculation of a drift for that, I got 0.66 inches. And again, compare it to something, whatever decision you want to make, whether this is a good drift or a bad drift. And so we end up with this structure. Right? All the columns are W10 by 39. The beams are W16 by 31 and W18 by 46. All right? So, what kind of a conclusion do we draw from this? Well, this flexible moment connection approach, I think, is a viable approach. It's something that you can do in a simple way. It's certainly a more simplified approach than a complete PR analysis might be. It potentially can give us an economical solution. I believe it satisfies in a general way the AISC specification. Perhaps the most critical part is that I think it's a good starting point. Okay? It gives you a way to maybe understand how these structures behave. Maybe make some decision as to whether you want to try to understand more about how partially restrained connections fit into a frame, fit into the economics of designing this system. Okay? I think there's a lot of potential. Would I design a structure like this and then go and build it the way I did it here? No, I would not. But I think it gives you a good starting point. Okay? The hardest thing is getting a start. Now I know my students would rather put it all in the computer and push the button. All right? Because they don't ever like to make mistakes. I'd rather see them take some kind of a simplified approach and get a start that may be reasonable. I thank you all. You must have a lot of energy to have stayed until 4:40. I know I am worn out. I hope you come back next year. As you've heard, I'm sure this is the largest attendance NASCC we've ever had. And of course, you know, Scott Melnick is never happy, so we're already looking at increasing the numbers for next year. Thank you very much. And I'd be happy to answer any questions, but I'm not sure you want to stay, so if you want to just come up and ask them, that might be more effective. And Cindy already had to rush off to her airplane, so I'm the end.